one-liner too. Thank you.
Thank you, Aitish, and hope you can make it to the final discussion. Thanks a lot for this. So let's move on to the final speak before lunch, and that is our own Aila Särkkä, who will talk about a sweaty subject. Please.
Yes, let me share the screen first.
Could I also, before you start here, if you are able to share your pictures, that's even more pleasant for the speaker to get the facial feedback, as all teachers know here in the Zoom era. So please add your movies. Thank you.
So can you see the full screen now? Because usually I have to do this twice.
Yeah, not to, well.
Okay, then I do it again, so hopefully.
It was large, but not completely full.
Yeah, let's see what happens now. Is this
that's
better?
perfect. Thank you.
Okay. So thank you, Torbjörn. It's very nice to be one of the speakers here. I have really enjoyed the talks we have had so far. This will be something different, but on the other hand, I noticed that Philip and I are partly using the same toolbox. So the work I will present is joined with Mari Myllymäki and her PhD student Mikko Kuronen, who are at the Natural Resources Institute Finland, and then with Adam Löwenbrook, who is a neurologist at the University of Minnesota. And he's the one who has provided us with the data and the original question. So I will start by giving some background on something that is called peripheral neuropathy and the diagnosis of it by using sweat tests. So that's where the sweating comes in. And then I will present the data that we have from the sweat tests. And for the data, in fact, we see some spots of sweat on the skin, and they look like point patterns, and that's why we thought that we could use point process models for the sweat spots and also for the activation of the sweat glands. And we have introduced two models. The first one is a sequential point process model, and I have added with noise, and I come later to that, what is the noise that comes in. And then the other one is something that we call generative point process model. I'm not going into details to them right now, but I will explain them later what they are. And then we fit both these models to the data that we have and see how they look. And if we, to look at the goodness of fit of the models. And then I conclude by saying something, for example, how we could go further. So what is peripheral neuropathy? It's damage to your nerves or some disease affecting your nerves. And this disease weakens the sensation. For example, if you think about diabetes and diabetic neuropathy, you don't feel as well when you have the neuropathy, but it also weakens your gland and organ functions. And sweating, you have sweat glands where the sweat comes, and that is sort of a gland function. And therefore, if you suffer from peripheral neuropathy, often you sweat less than a healthy person. And common causes for this peripheral neuropathies are, for example, diabetes, chemotherapy, radiation therapy, or if you drink too much alcohol. And then there are several ways to look at the damage that your nervous system has gotten. And one way to look at it is to measure the sweat gland function, which we are doing here. I also mentioned that you can also study the structure of epidermal nerve fibers, which are the nerve fibers on the outmost layer of your skin. And I mentioned this because we have also studied that at the department, and we have, for example, 2 PhD theses done in that area. But here we look at the sweat gland function, and there are several sweat tests that can measure this. And the one we are looking here is the sweat test that was developed at the University of Minnesota in the group where Adam is. And so they developed a test, and this test can measure the density and distribution of activated sweat glands, and then also the sweating rate per gland and per skin area. So what they have a camera that they use to measure how much you sweat, and then they see the whole sort of temporal appearance of sweat glands and so on. And what they did in their first study, they compared sweating of healthy controls and patients suffering from diagnosed diabetic neuropathy. And this image here is from this article. And this first one on the left, that sweat spot picture is from a healthy subject. And then these two others, B and C, they are from a diabetic patient who is suffering from neuropathy. And when they compared these, and mainly they were using sort of, or they were all using some measures, for example, how much they sweat, but then also they were looking at these pictures visually and made some visual observations. And then when they saw, based on many plots from many patients, that typically for healthy controls, you see a rather regular pattern of black spots. So the black spot is sweat, and which is distributed on the whole test area pretty uniformly. And then these, if they look at the single spots, they grow fast, and then they emerge within a pretty short time. And then you get these large wet areas. So I would suspect that this picture here is not really in the end of the video, but it's sort of in the beginning when it's not so wet yet, but you can still see that there are a lot of spots. But then if they look at the patients suffering from diabetic neuropathy, they see that the overall pattern of black spots is less regular, and they saw some holes. So the holes here are marked with these little white stars, that they think that there are more holes in the pattern of the neuropathy group. And somehow what they were thinking was that somehow, since there are more holes, the spatial pattern is not the same. So the hypothesis was that these neuropathy patterns are not independent thinnings of the healthy pattern, but something else is going on, that the sweat glands activate in groups or something like that. And then also, if they look at then the amount of sweat, they saw that these sweat spots of a neuropathic patient they are growing much slower, and there is not as much wet area. So these were their results, but somehow when they saw these holes, they were thinking that the spatial pattern in the healthy and in the neuropathy cases are not the same. And that's why they somehow talked about it and said that maybe one should do some spatial analysis. And this is how we came along. So then the data that we have. So you saw these images, so they are just snapshots of the videos they have. So what they have, they do so first they make your sweat so that they can measure your sweating, and then they cover your skin in some starch or something, and then they put a camera on it, and then they put the starch so that they can see the sweat, so that the sweat becomes these dark spots. And they take videos recorded at the rate 1 frame per second, and they film that for 1 minute. And they cover a small area, approximately 13 times 17 square millimeters. They take these videos from different body parts. In this case, it was foot and calf, sometimes both. And they have altogether done this for 120 healthy controls, and then 65 patients suffering from peripheral neuropathy. And some of them had a diagnosis, so 18 out of the 65 had a diagnosed neuropathy, and the rest had a suspected neuropathy. And here they don't know the cause. So there were like chemotherapy patients, diabetic patients, so everybody was in the same group. Now, we don't have access to all these videos, but we have access to 15, 5 from each group, meaning 5 healthy controls, 5 suspected neuropathy cases and 5 diagnosed neuropathy cases. And then we looked at these videos and tried to do some kind of statistical or spatial statistical analysis of them. And here you have 4 snapshots of one of the videos, and this person is healthy. So you see it in the end that the area is pretty wet. And if you are healthy, then in fact, already at 1 second, during the first second, there are a lot of sweat glands activating, meaning that you start to see these sweat spots. They are first very small, they grow, and then in the end, the area is pretty much wet, even though there's still some dry skin as well. And there are, even though here there are quite a few glands that have activated during the first second, there are more coming if you go as time goes by. But this is sort of the idea. You get more and more spots and you get more and more wet area. So what we then did, we wanted to look at these as point patterns, so realizations of point processes, and we needed to extract the spot centers. And we developed an image analysis approach to do that, and I'm not going into details to that, so I just show you what the final point patterns look like. So these are the point patterns that we extracted, and this is the final result after 1 minute. Of course, we can extract the point patterns after every second, but these are the final ones. And here you have the controls on the top row, and then the suspected neuropathy patients, and then the diagnosed patients on the bottom row. And here one of them is sort of smaller, and this is because the video, it seems that it has been damaged on one side. Maybe the camera had moved or something, but we decided that we didn't really trust on that part of the video, so we cut the area. So these are the 3 groups, and somehow we wanted to now see, is there any difference between the groups now when it comes to the spatial structure. And we started by doing what Philip was doing. So we estimated the pair correlation function for each group. And as Philip said, somehow it measures how likely it is to have 2 spots at some distance. And here, if you have values less than 1, it's indicating inhibition or regularity, and the values bigger than 1 indicate clustering. And then in the Poisson case, if there is no interaction at all, it equals to 1. And here, these curves that we get are very typical in a regular pattern. So there is some small scale inhibition, and then somehow when there is some range of interaction where that comes, after that you can have more points. So there is inhibition in each group. If you want to look at differences, maybe if you compare the blue curve to the 2 others, and the blue curve being the diagnosed group, there the initial peak is at slightly longer distance than in these 2 other groups. So based on this, there is some indication that the spatial patterns may be not completely the same in these groups. And then you also see something here at small distances, and there seems to be a difference between the normal group and the 2 others, and I come back to that. This is in fact related to the noise that I was talking about in the beginning. But let's now ignore that part. Okay, so now we have an idea that there is sort of that we are looking, if we want to model these point patterns, we are looking for regular models for regular point patterns. And now we also wanted, somehow there are models for them. For example, say Gibbs point processes are often used. But here we also wanted to look at the temporal development of these point patterns. And that's why we decided to use the so-called sequential point process models. And the way we define them, we follow the definition by Antti Penttinen and Hanna-Kaisa Ylitalo, who suggested these models for eye movements. So what they do, you'd have the number of sweat glands in our case that have been activated, and we know that. So we generate that many points sequentially. So we start by putting the first gland uniformly in the area. And then the next glands, or the next gland locations, we pick with the probability density given everything that is already there. So if we are putting the next gland position, we are suggesting xk, some coordinate or location, then we do it conditionally on everything else. So the xk minus 1 arrow is the vector of all the other glands that are already there. And then we can write the joint density so that we take the product of these conditional densities, and then the first 1 over area of the window is the contribution from the first point that we put there. And now, of course, we somehow we don't observe every gland that it's appearing, because we measure only once a second. But still, you can think that they all have their individual times, and it would be the model for the process itself. So now what we should do, so now we just have some probability density here, but now we should choose that so that it fits into our sweat gland activation situation. And there we know that the pattern is regular, so we want to have a regular model. And in fact, we first thought that we could take a hardcore model, meaning that we have some hardcore distance, the minimum interpolate distance between the glands, and then we don't allow any neural gland location closer than that to any of the existing ones. That model wasn't really flexible enough, and that's why we thought that we need some soft interaction. So we can allow very close pairs of points, but they have very low probability of appearing. But then as the distance increases, the easier and easier it is to add points there. And this soft core density, this is also, we chose this one because it's sort of used, for example, in the Gibbs point process theory. And here we have two parameters. We have R, which is the interaction range, telling something how likely it is to be at certain distance. And then we have the soft core parameter kappa. This is a parameter that somehow this is between 0 and 1, and it tells how soft core or hardcore the model is. So when it goes to 0, then we obtain the hardcore process, meaning that there the 2 points can't be closer together than this distance R. But the closer the 1 it is, the more soft core, more closer to Poisson process the model is. And this one here is the scaling fact. So now we have a model with two parameters, interaction range and the soft core parameter kappa, and we should estimate those. And in our case, we are lucky, we can write down we have a density function, we can write down the likelihood and use the traditional maximum likelihood method to estimate the parameters. It's a little bit confusing, by the way, that if I see ML, I still think about maximum likelihood and not machine learning. But that's a problem with abbreviations. So here I have just written down the log likelihood function. So it's this one here where you see the parameters, and then you maximize that with respect to R and with respect to the kappa and get estimates. And now usually it can be difficult to compute the scaling factor, but in this case, it can be computationally expensive, but Mikko found a pretty efficient way to do that given the particular sum form that the conditional density has. So it was pretty quick to compute this. And then we estimate the parameters, and then a very typical way in spatial point process analysis to look at the goodness of fit of the model is to take a summary statistic. In this case, we took the pair correlation function. You estimated it from your data, and then you simulate from your model, and you estimate the same summary from the realizations, and then plot some kind of envelopes. And then you check whether your data is inside or outside the envelopes. If it's inside, you are fine, the model looks good. If it's outside, then you may have to think for a better model. And here we have plotted them separately for all these different cases. And especially if you look at the healthy controls, which are on the top row, you see that the model is not, it doesn't fit so well. So first of all, there is sort of like the uphill is not, the first uphill is not really caught by the model. You would sort of like to push the envelope to the right to get a better fit. And also the first peak is not caught. So you see that the envelopes are very flat. It doesn't really follow the shape of the database pair correlation function. So we were not so happy with this fit. And then also here again, we see the first pair correlation functions were pooled. So one pair correlation for group, but here you see even more clearly that at short distances, especially in the control group, you have some pairs of points and maybe they shouldn't be there. And then, so this is again these pooled pair correlation functions. And you see the same thing here, that you have these sort of a little bit unexpected close pair of glands, especially in the control group. And then when we looked at the videos more carefully, we saw in fact that there were some close pair of points that shouldn't have been there. So they were detected by our image analysis approach as 2 points, even though there was only one. And I tried to explain this I zoomed in one of the videos. And if you look at this spot here in the middle, so in fact, it is one spot, but the image analysis approach recorded is as 2 spots. And the reason is that you see sort of this grid-like structure of your skin under here. And then what happens when this spot came first and it starts to grow, but when it comes on the other side of this grid structure, it's sort of, there is sort of like a ditch. And then when it goes to the other side of the ditch, the image analysis approach thinks that there is a new spot, even if it's not. So that's why we get these falsely recorded close pairs of spots, even though there is only one spot. And of course, we could improve the image analysis, but we should almost do it manually. But for 15 videos, maybe we could have done it. But if you are looking at 120 or 500 videos, then it's not really doable. And then somehow making it automatic, at least we couldn't find an easy way to do that. So that's why we thought that, okay, but there is this, and this is what I call noise. So these extra glands that appear next to some bigger glands, that they are not really real. And those are our noise glands. So what we did, we added the noise part into the model. So we had these conditional densities with the soft core density to add new points. So then we thought that either we add a new gland according to this soft core density, or we just put some random noise. So we put random noise, just a pick point randomly on the area with probability theta, and with probability 1 minus theta, we take the point according to the soft core model. So then we get an additional parameter, this mixture weight, to estimate. And here are the parameter estimates. And now here everything was done by maximum likelihood. And first we can look at the parameters estimated without noise. So these are the pluses, and then we have only the interaction range and the soft core parameter kappa. Then we didn't have this mixture weight at all. And if you look at these here, it seems like in the control group, the top row, the kappa, meaning that the higher the kappa value, the more soft core the model is, further away from hardcore. So it seems that the models are more soft core, or the patterns are more soft core in the control group than in the 2 other groups, even though there is, of course, a lot of individual variation. And then also there's the difference between in the interaction range. It tends to be slightly smaller in the control group compared to the neuropathy groups. But if you sort of take into account that there are these extra close pairs of glands that have been observed incorrectly, and you use a mixture model and add some noise, if you look at the circles here, in fact, don't seem to be any difference on the two parameters, kappa and R. The only difference is when you look at the mixture parameter. So then there is sort of like it seems that there are more of these extra points in the control group than the two other. So in some sense, the noise explains the difference between the groups. And this is an example how the goodness of fit of the models look like. So this is one of the, I think, this was one of the healthy cases. And here you have the goodness of fit of the model without noise, and we saw that it didn't fit so well. If you take the noise into account, it fits much better. So it catches the first peak, and it at least almost catches the first uphill. It doesn't fit here, but the reason is that we are believing that we wanted to model the sweat glands and not the noise. So that's why we simulated the envelopes without the noise. So we just used the new soft core parameters and simulated the envelopes. And that's why we didn't even expect it to fit here, because these points are not real. And here you see the goodness of fit for all 15 patients or subjects. And here you see that in most cases it works pretty well. There are some cases here and there when the first peak is not completely caught. But this looked quite nice. And I think this would be one possibility to model it. But then we were thinking that somehow now we now know what we observe in the end. And we are sort of, we know that a certain number of sweat glands are activating. So we simulate that number of glands and then we compare. And we thought that another way would be that we start from what we are not seeing. So there is some underlying structure. You have your sweat glands in reality. It's just that we don't observe them all necessarily if they don't activate. But we thought that we could start from that we don't see, and then have what we see as a thinning of the underlying unknown pattern. And this is what we call a generative model. So this is a sort of a different way to look into the problem. So what we here do, so we first model the underlying unobserved sweat gland pattern, the true one, and then activate the activated sweat glands that we observe by thinning the underlying gland pattern. And again, we believe that the underlying gland pattern, it's some kind of a soft core pattern. And now we don't know the number, so we can't just simulate a certain number from our soft core or some soft core model, but we have to have some other stopping rule. And that's why we thought that we just keep on adding points as long as they fit. And but if you have a soft core model where you can there's always a possibility to put 2 points very close together, you can keep on adding points forever. So it never gets filled. And that's why to construct the underlying soft core structure of the sweat glands, we generated first a hardcore model. So we added points sequentially again, one by one, and we always had a minimum hardcore distance between them. And now this hardcore distance is R. And we kept on adding points until there was no space left. But this gives you a hardcore structure. And somehow to get the softcore structure, we disturbed this hardcore model so that we added for every location, we added some Gaussian noise with a variance sigma squared. And then we sort of, the whole model was sort of disturbed so that we got the soft core structure instead of hardcore structure. And that was our way to generate the underlying gland pattern that we are not observing. And then the final observed pattern is that then we start to independently thin with some activation probability P. So for every gland, we have a probability P to activate it and 1 minus P not activated. And then we got a pattern that corresponds to the pattern that we see in the end of the video. And now this model, we have 3 parameters. We have the hardcore distance of the original hardcore model. Then we have the variance of the Gaussian noise that we are adding to the locations to get the soft core. And then we have the activation probability. And now the problem is that this model becomes so complicated that we can't, at least we weren't able to write down the density function and the likelihood. And now we can't use maximum likelihood method anymore to estimate these. And now I go to Philip's toolbox again. So we use the approximate Bayesian computation here. And now I say a little bit more about the method in case somebody doesn't know. So here, why we use that is that if you have a likelihood, then you can use either the traditional maximum likelihood method, or you can use likelihood-based Bayesian inference. But if you don't have the likelihood, then if you find a model that you can sample easily, and in our case, we can sample from our generative model very easily, then the approximate Bayesian computation method is very nice, because it's based on sampling from the posterior, or in some sense, pseudo-posterior distribution. So there you take, and I think Philip mentioned this too, so you are looking at some summary statistic that you choose, and of course there the difficulty is which summary statistic to use, but somehow that you are looking at the probability that the summary statistics computed from your simulation, model-based simulation, and the summary statistic from your data, that the difference is very small. So it's and you sample from this posterior type distribution. And then this being very small, then this epsilon here is the tolerance level that you have to choose. In fact, we had a very nice talk about choosing that in the last week at the statistics seminar. And a very simple algorithm for this would be that if you want to sample, say, M sample from your posterior distribution, what do? You take a parameter from your prior distribution, or parameters from your prior distribution, and then you generate a realization. So you generate a point pattern using those parameters. Then you compute your summary statistic from your simulated pattern and from your data, compare them, and if they differ less than this tolerance level, then you accept it in your sample, otherwise you don't, but you do it again. And then you do it until you get the number of samples as you want. So this is a very simple algorithm, and I think there are many ABC algorithms that are better than this, but I think this gives you the idea. And here we use something that is called an adaptive ABC-MC-MC algorithm. There, in fact, you don't have to fix the tolerance level. Instead, you simulate a very large number, and then you take the ones where this difference here is the smallest. But then we have to choose the summary statistics. And there are some papers where they recommend, now we have not only one parameter, but 3. And then maybe one summary statistic is not enough. And we could use the rule of thumb from this Lee-Fernhead paper that maybe you should choose approximately the same number of summary statistics as you have parameters. And we first thought that we could use the whole because the pair correlation function is telling a lot about the spatial structure, so we could take the whole function, but this is not really recommended. So we decided to take 2 points from the pair correlation function, and this may be, now I don't remember what Philip was using, but I think he was thinking in a similar way at least. So if we go back to this picture, for example, so what we didn't use the whole pair correlation function, but we decided to use points from this. And what we would like to, somehow, if you think about the hardcore radius and the softness parameter, somehow the parameters in some sense of the softcore model, somehow the first uphill and the peak, the location of the peak, they tell a lot about that. So the peak, for example, tells about the hardcore radius, and then the slope tells about the softcore. So that's why we took 2 points from the pair correlation function, or we in fact took the x values here. So, and we are looking at, we sort of thought that we could take the location of the first peak, but it can be hard to estimate. Here it's not, it's pretty easy, but there are cases when it's more flat. So that's why we didn't take that, but we took the smallest distance where the pair correlation function gets the value 1. So it would be this distance here. And then to get slope, then we took another point, and then we took the distance, the shortest distance where it reaches 0.75. So these distances here would be pretty close together. So those are 2 summary statistics that we chose. And yes, I should also point out that I said that it's the smallest distance where you reach either 0.75 or 1, but also the distance has to be large enough, because at short distances, this estimate of the pair correlation function is unreliable. So we have used kernel estimation there, and there can maybe you saw in some of these. Now you will see soon that the estimation at short distances is not really reliable. And then to get some idea of the activation probability, then we could take the number of points, the number of gland locations that you observe, but there we need that there are some extra, we know that there are some extra points, and that's why we didn't want to take the number of points, but we looked at the empty space function instead. So empty space function is sort of its own probability. So it's a distribution function which tells you what is the probability of, if you have an arbitrary point, what is the probability of having a point of the process at certain distance. So then we here took 1 point from that function, namely the smallest distance where this function reaches the value 0.5, or, and it, yeah. And then here you see, so then we estimated this using the ABC method. So the 3 parameters, the hardcore radius, and here is the standard deviation of the Gaussian disturbance, and then the activation probability. And if we compare, now again, the 5 first ones are the control group, and then the neuropathy group without diagnosis, and then the neuropathy cases with the diagnosis. And the softcore parameter, or the disturbance Gaussian variance, there we can't really see any difference between the groups. But if you look at the 2 other parameters, somehow look at where this posterior distribution is concentrated. So there's a lot of within group variation, but maybe there is some tendency that the hardcore radius is a little bit smaller in the healthy group compared to the others, and maybe the activation probability is higher in the healthy group than in the others. So you can see some differences, but they are not very clear, and there is a lot of variation within the groups. And here are the similar type of goodness of fit test as we did before. So we now the envelopes are from the posterior distribution. And here again, we see that the model fits quite well. and in fact it looks, the goodness of it looks a little bit better than of the sequential, the first model, but still there are some cases where it's not perfect. And here in fact you see the problem with the pair correlation function, that that the model has a lot of flexibility, so here the at short distances it's not really reliable. But this model seems to be quite nice. And here it just somehow see how the patterns look like. So the top row, you see 3 of the data cases, a control pattern, a suspected neuropathy pattern, and the neuropathy pattern. And then the bottom row, you have the simulations from the model. So if you just compare them visually, you may see that they look quite alike. But one thing that is interesting, that if you look at the, for example, this pattern here, you see that there are some sort of holes in the pattern as you have in the data. And these were the spots that they, in the first paper from the Minnesota group, they were saying that somehow the spatial structure is different. And maybe the activation is not sort of independent of location. But here, in fact, we did an independent thinning, and somehow even the independent thinning, independent activation would create these holes. So that's why their original hypothesis may not be correct. But I think there is a lot still what we have to think about and how to interpret the results that we see. And then I just wanted to conclude. So we have introduced 2 ways to model the activation of sweat glands and to take the noise, these extra glands, into account. So first we had the sequential softcore model with noise, and then we use likelihood-based inference. And the other way was to start with modeling the underlying sweat gland pattern that we don't observe by using our generative model. And here, in fact, we didn't put any noise in the model. So the noise there was just to disturb the points, but it was nothing to add extra points or something. So we didn't really take the extra points into account in this generative model. But instead, when we used the ABC approach to estimate the parameters, we chose the summary statistics so that they were robust with respect to the noise. So in some sense, noise was taken into account in the inference part and not in the model itself. So then, especially when we looked at the generative model, there was some indication that the parameter estimates are not exactly the same in these, especially when you compared healthy and neuropathy groups. But I think we have to still think, what does this mean? For example, you can think that if you look at the underlying skin and the gland structure, shouldn't that be the same for everybody? And then if you get differences there between the groups, why do you get that? Maybe the explanation is that in fact the thinning is not independent. If we had a different kind of thinning and started with the same pattern. So I think there's a lot of things that we have to think of. And therefore, for example, that if it really is so that the underlying sweat gland pattern is not the same for everybody, is it due to some non-spatial covariates, for example, body mass index? So maybe we should include some other information into an analysis. And of course, I mean, we saw that there was a lot of variation within the groups. So I think it would be nice to get more videos and not only these 15. And also here, we haven't looked at the size of sweat spots at all. And we started only by looking at the locations of the sweat spots, but not the size. And this would be something also that could be included in the analysis. And I think there are some references, and I just would like to thank you.
Thank you. Thank you, Aila. Really great to hear about this. And we have still a few more minutes to take some questions, or for Aila to take questions on this. I know I just checked out the chat room, there was nothing there, but
Sorry, I have one question.
Oh, you have one? Yeah,
yeah.
I'll have one afterwards.
Okay.
Go ahead, Philip.
Yeah, so thanks for a nice talk. It's interesting to see that there's overlap between what we're doing. So I was wondering, in your pair correlation functions, do you see some sort of oscillations after the first peak? I'm not sure if you talked about that specifically, because that's sort of, it's an indication of that you have some sort of periodic structure in your data, right? Have you looked further?
It's often, if you have a pure hardcore process, it tends to be like that. That somehow that you have the first points come at some specific distance, and then again, because they sort of then repel other points, then the next one comes 2 times that. So I think this, for example, this one here, it must be pretty close to hardcore.
Yeah.
But then here it's more, when it sort of is more flat. Here, for example, it's not as clear. But I think the periodicity can come from that is very close to a hardcore process.
Because your model shows some, I mean, you have a, it seems at least like you have a, because the dashed line is the model.
Yeah, the mean. Yeah. Yeah.
So you have at least like a local minima after the first peak, but then it doesn't, the correlations don't seem to span, they don't seem to be as far away as the data.
Yeah, and I think it's the soft core.
Okay.
It's a soft core. If it was a hardcore model, I think then you would see the humps.
But the hardcore model wouldn't really work with the data then?
No. So we started with that because we thought that that's the simplest, and it didn't really work.
Okay. Thanks.
Thank you, Philip. So the last thing you talked about in the discussion about the thinning process. Yeah. Have you talked to any biologists about that? Because maybe there is some real anatomy reasons to gain some insight for the model there. What happens?
You mean whether it's independent thinning or not?
Yeah, I mean, if, for example, if you have this illness that you have more thinning than the healthy subjects, for example.
Yeah, in some sense that we see, where is the here? So if you look at the thinning, this is the activation probability. And the activation probabilities tends to be higher in the healthy group,
right? Yeah.
Than here. Yeah. Even though with 5 people, it's not so easy to see, but somehow there's more tendency. There is one outlier here, but otherwise they tend to be on the closer to 1. And in the neuropathy groups, they are less than 1. So there are less sweat glands activating in the neuropathy groups.
So maybe I was after more over that. If you have a system here, then if you have an inactivity here, will it be higher probability? What's the correlation between these thinnings? In a sense, could maybe there are some underlying anatomical reasons to look for correlations between thinnings as well, not only randomly.
You mean?
If you have one that is being destroyed, maybe there is a lower probability that the neighboring will be destroyed as well, or will it?
Yeah, exactly. And this is what we suspected, because I mean we thought we took this independent thinning because it's simplest, and we thought that let's just see what happens.
Okay.
And then we were a little bit surprised that it worked.
It was good enough. Okay.
Yeah. But somehow, and because our idea was that we start with an independent thinning, but it can't be independent because their hypothesis at least said something else.
Right.
But now it seems that at least here we can create something similar looking by using independent thinning. Right. But then it may be that if we started instead, that we sort of say that we estimated the underlying unobserved pattern the same for everybody, and then looked at the activation, then we could see that independent thinning is not enough. And I think that's something maybe to look at next.
Right. So a very last question before we go for lunch here, that can you go back to an early picture when you looked at these different seconds, 0 and 20 seconds, and so 2 questions there. I mean, it looks like it would be an interesting measure to see when between 30 and 60 seconds in this situation, where do we have percolation in this system? And the number question is that has your husband asked you that already?
No, he has.
Okay.
But yes, that's
That would be
I don't know. I don't know if it would mean anything, but it would be an interesting question.
Good. Okay. Thanks a lot for this. Oh, okay. Great. So no more questions in the panel here, and we have then a lunch break until 1 o'clock. We start 1 o'clock sharp again. Thank you very much.
Yes.
Okay, and you can see my slides, right?
Yep.
Okay. So thank you very much, Philip. It's very nice to be here. Thank you very much for the invitation to talk and to share some. So I will mostly share some a recent study that we did specifically on trying to predict metastatic relapse